So hydrolysis is one of those things that happens when we take a solid, ionic solid, and put it into aqueous solutions and actually get an acid or a base. So let's consider a simple example, sodium cyanide. If we take sodium cyanide and put it into solution, it dissociates into sodium and cyanide ion. That's how we remember that, is because remember the name. And sodium cyanide, when you actually put it into solution, it actually makes a basic solution. So the question is why? Well, sodium cyanide dissociates, and so we put a little equal sign because we know this goes completely to the right. This isn't really an equilibrium, it's just all sodium salts are soluble. So it dissociates into sodium ion and cyanide ion. And so let's consider those two things. So cyanide, we know, acts as a base because it reacts with water, because it's an aqueous solution, and forms hydrogen cyanide and hydroxide ion. And sodium ion is an acid, and because it reacts with water to form sodium hydroxide and hydronium ion. So all these questions, this hydrolysis question, comes back to the same thing of, all right, so I dissolve my solid and dissociates into two things, and one of them is an acid and one is a base, and we have to sort of determine which one of these is more significant. And the way we do that is by looking at the strengths of the conjugate. So hydrogen cyanide is not a strong acid, so that means this equilibria, this first equilibria, it has some portion going to the right. So we actually have some population on the right hand side. So we have some hydroxide ion coming from this first equilibria. In the second equilibria, however, sodium ion is the conjugate of sodium hydroxide, which we know is a very strong base. So this equilibrium here lies very far to the left. Since it lies far to the left, that means there's very little hydronium ion, and so the hydroxide ion sort of dominates. So this is the entire concept of hydrolysis, that these soluble ions form acids and bases in aqueous solutions with the water. And as long as you have a soluble ion, you have acids and bases. And so we're going to compare the relative strengths of those acids and bases to sort of predict what will the solution be, acidic or basic. And it can get complex, but we're not going to go that complex. We know that hydrogen cyanide has a Ka of 10 to the minus 10, which means that cyanide ion has a Kb on the order of 10 to the minus 4, where we know, and we also know that sodium hydroxide is a very strong base, so its Kb would be essentially infinite, so its Ka would be essentially 0. Right? So when dissolving ionic compounds, the cation is almost always an acid, and the anion is almost always a base. And we're looking at the relative strengths. So let's look at a couple more examples. Sodium chloride dissociates into sodium ion and chloride ion. We know that sodium is an acid. Its conjugate is sodium hydroxide. And sodium hydroxide had essentially an infinite Kb value. So that means sodium ion, as an acid, is very, very weak. We know that chloride ion is a base. It is the conjugate of hydrochloric acid, whose Ka is infinite. So that means that chloride ion is a very weak base. So I have a very weak base, or it's essentially a non-existent base with a non-existent acid. So the solution remains neutral, since we have, yes, I technically have an acid and a base, but they're both worthless. So there's nothing. Ammonium chloride dissociates into ammonium ion and chloride ion. Now ammonium ion is an acid, and we can actually calculate the Ka value. So the Ka for ammonium ion is Kw divided by the Kb of ammonia. The reason why we're doing that is because the Kb of ammonia is one of those table values. And if we actually go and find the value for Kw value of Kw and divide by the Kb of ammonia, we get a value of 5.6 times 10 to the minus 10. So that's the Ka value for ammonium ion. Chloride ion is a base, we know that, and we can calculate the Kb of it by taking Kw and dividing by Ka of its conjugate, which is hydrochloric acid, but the Ka of hydrochloric acid is effectively infinite, so 1 times 10 to the minus 14 divided by infinity is big fat 0. So the Ka for our acid in solution, which is ammonium ion, is 5.6 times 10 to the minus 10. The Kb for the base in that solution is 0, since there is the strength, if you will, of our acid is greater than that of our base. The overall solution will be acidic. sodium acetate. So sodium acetate dissociates into sodium ion and acetate ion. We know that sodium ion is the conjugate to a strong base, which is sodium hydroxide. So that means that sodium ion is a non-existent acid. We know that acetate is the conjugate to a weak acid, acetic acid. So acetate ion is a weak base. So we have a weak base with a non-existent acid. So the overall solution is basic. Ammonium nitrate. Ammonium ion is the conjugate of a weak base, which is ammonia. So ammonium ion is a weak acid. Nitrate ion is a conjugate of a strong acid. Nitrate ion is conjugate to a strong acid, nitric acid. So nitrate is a non-existent, really, really weak base. So overall acidic. So let's look at a slightly more difficult example. Ammonium cyanide dissociates into ammonium ion and cyanide ion. Ammonium ion we know is an acid, and it's the conjugate of a weak base, which means that ammonium ion would be a weak acid. Cyanide is a base, it's the conjugate of a weak acid, hydrogen cyanide, so that means cyanide is a weak base. So we have a weak acid and a weak base. So in this case we actually have to be a little bit more quantitative. So we have to look at the relative strengths of each one of these, the ammonium ion and the cyanide ion, by looking at the Ka and Kb values. So we need to know the Ka of ammonium ion and the Kb of cyanide ion. But we're not going to be able to find those, but we can find the Kb for ammonia and the Ka for hydrogen cyanide. These are table values. So the Ka for ammonium ion is 1.0 times 10 to the minus 14, so Kw, divided by the Kb of ammonia, so we get 5.6 times 10 to the minus 10. The Kb of cyanide ion, take Kw divided by the Ka of HCN. Again, these are table values, this and this. So 2.0 times 10 to the minus 5. And so now what we basically have to do is compare these two values, the Ka of ammonia and the Kb for cyanide. So it looks like cyanide is a stronger base because its Kb value is greater than that of the Ka value for ammonia. So our solution, when we take ammonium cyanide dissociated into solution, it is basic. Now, we can, if we wanted to, do this a little bit more quantitatively and actually calculate, say, the pH of a 0.015 molar hydrogen cyanide solution. And this isn't something that I would ask you to do in our class, but I just want to show you, sort of like show how it's done. So here are our two equilibria. So we have ammonium ion acting as an acid, and we have cyanide acting as a base. And we can determine the K values for these things, and these are those same values. So technically this is the Ka of ammonium ion, and this is the Kb for cyanide ion. And one of the things we can do with equilibria is we can combine them. We can combine these two equations and come up with sort of an overall reaction. So the rules are we can calculate the value of K by, when we add two equations, we multiply the K values. So this is sort of like the overall reaction, if you will, and the K value is just the product of the two source reactions. And so now we have a K for this new reaction. The problem is that these it's sort of like two independent reactions, but we're solving it as one large equation. So this is sort of our initial amounts. So I guess I'm doing calculation of 0.30, and the question asks for 0.015. So that should be 0.03, or 0.30, not 0.015. So 0.3, 0.30000, and it shifts to the right, and the cyanide goes down by some amount x, but the ammonium ion does not. These are not tied together because they come from two independent source reactions. So the amount that this goes down by is different than the amount this goes down by. But we can sort of adjust it, so I know the hydrogen ion is tied to how much cyanide goes away, and that the hydrogen cyanide is also tied to this. That's why I have an x and an x and a y and a y. And so I can put this into my new K expression. It is equal to 1.1 times 10 to the minus 14 is equal to all of this huge mass, which if I drop in my E line, I get x squared, y squared divided by 0.3 minus x, 0.3 minus x. Just hairy and nasty. So what that means is we have to be able to do this, but we also know that hydrogen ion times hydroxide ion is 1.0 times 10 to the minus 14, which is x times y, And so we can actually do the calculation. So with Wolfram alpha, we can calculate the x, y squared. We actually plug this in and solve for the equilibrium concentrations. Now again, this is sort of like, the calculation is sort of beyond the scope of this course, but I wanted to show you how you can solve two equilibria at once.